So how do you separate some of this stuff? Because that gets to be a big problem. How do I separate any of the stuff that I'm going to work with? You know, if I have a mixture, how do you get rid of it? And can I apply that electrolysis thing? Well, you could do that, but a chemical, that might chemically actually do something to some of your substances within your mixture. You don't actually want to do that too much. Heating it up can have the same result. If your idea was to separate a sugar from salt, and you decide, well, I'll just heat it up. Well, that's going to be a problem. You're going to caramelize the sugar first, and that's going to be a big problem because you didn't want to do that. Well, one of the biggest ways to do it, obviously, is filtration. You take a piece of filter paper, and with that filter paper, you can run, generally speaking, the heterogeneous system through it, and through the filter paper. And as you pour your liquid down in here, the liquid kind of sits in here, starts dripping down, so you start getting water droplets and liquid droplets through. I don't want to say just water, because if it's homogeneous will not get separated by filtration. And so these liquid pieces go into here. The solid pieces will stay inside of the solution and not go through the filter paper. So essentially in the end, what you have here is you have yourself solid sticking on the filter paper, the heterogeneous part that was making your system pretty heterogeneous, sticking on the filter paper, while the remaining solution or liquid layer actually can just go right through your filter paper. That happens. You brew coffee, you've used filter paper, you've used this technique to do it, made iced tea. The bags around them are actually the filter paper that you're using. So filtering is a common thing we use to separate, a phase of like a solid or something like that away from a liquid phase that may or may not be a solution itself. But it separates those two. Okay. The problem comes to be if you want to separate a homogeneous solution. Those get to be very tough because you have a really very well mixed system. In fact, the things have dissolved into one another. And so when you have a solute dissolved into a solvent to make a solution, the problem you run into is you can't just filter it. It would pass right through that filter paper just like anything else. So how do we deal with that? There's a couple ways to deal with it. The number one way to deal with it is simple. Let's just boil it off, especially if it's a liquid. So what process we're talking about there is called distillation. Okay? What we would set up is we'd set a boiling flask up, and inside this boiling flask we put our liquid, that is our solution that we're looking to actually separate. This could be a mix of ethanol and water, common mixture that is very suitable by this process. And there's two types of distillation, simple and fractional. If you want to learn more about those, it's on the website. Check it out. They're really cool, but they work off to the basic same premise. And I'm going to show simple distillation here. So in simple distillation, you have this boiling flask set up, and you're going to heat it up. Usually put these things in called heating mantles. They're kind of like gloves that fit the flask, and they heat really hot, okay? And the goal there is to boil off it. Now, since ethanol and water have two very different boiling points, okay? These two different boiling points is going to allow us to separate it based off that boiling point. If you had two things that are very similar in their boiling point, distillation might not be the best way to go here, at least not simple distillation. Fractional may work a little bit better, but again, it all really depends on how close the boiling points are to each other. If they are still very, very close, this still may not be the method you want to go with. So we will take this flask that we're going to start to boil, and we're going to insert essentially this little kind of arm adapter here, which we put a stopper in here that has a thermometer, and this goes down to this weird like kind of tubey looking thing. It's usually hooked up to a little bit of cold water. Okay. And this tube essentially goes straight through, whereas this is called a water jacket that's set out here. This jacket allows water to pass in through here, and then essentially it comes out on the other side. This usually, this goes to the drain. You don't want that going around all your setup or anything like that, or on the table. That's not going to work out so well. And the goal of this is to cool, and we'll get into more in that in a second. And essentially you just have an adapter down here where you can let this drain into a beaker, a flask, or a test tube, whatever you're trying to collect it. And so what will happen here is as this boils, you're going to notice that this thermometer's temperature will raise up. Essentially speaking, and it's a little more technical this, but essentially speaking, what will happen is this will start boiling. And it'll boil at the lower boiling point, which in this case is ethanol. So your ethanol vapors are going to start to form mostly first, okay? Is it all ethanol vapors? Well, I can't say that for sure because obviously water does evaporate. We do affect how fast something evaporates as we heat it up. So the goal here is that we can at least get a lot pure form of ethanol out of this one. So these vapors go up here. This is going to start reading approximately the boiling point of ethanol. And the goal here is to get it so that you get a nice flow over here, that you're getting the vapors over, but they're not spilling over. If you're really, really heating this up too hot, you're really going to force the other solution, the other part of the solution, the water, to also come out. And you're going to get a higher proportion of water over there than you want. So as this comes over, this vapor comes into here, that hits the water jacket, which is that cold water now that's running around it. It's not going actually in that tube, runs around it. And that ethanol then liquefies, forms droplets, and drops right down into here. And that's pretty much distillation. Distillation, separating them out because they have very different boiling points. And that is that way. Sometimes you have to do this multiple times. Simple distillation, alcohols, ethanol, and water specifically. Sometimes they're talked about triple distilled alcohols and things like that. It really depends on what kind of purity you're looking for. You can get alcohol very pure. You can get it up into the 99.5 range, 99.9 range, depending how you do it, using molecular sieves or something like that. But traditional simple techniques probably going to end up at a 95%, and that's about where you're going to end it up at. So distillation is one of your common techniques. There's another one that also goes along in the organic world called fractional crystallization. We'll talk about that later. Another one you may want to look at is chromatography. Very elegant, very nice, can be your most tedious. Okay? How does chromatography work? Here's the basic idea. You've probably done maybe some paper chromatography in your past. And how does that work? Well, you put a solvent down here. You know, probably in the past maybe use some water. You put a piece of paper into this water. Okay? And before you put that piece of paper in the water, you've put a little pencil mark and a dot of the substance you have a solution of. If you've done this in the past in elementary school, middle school, it's probably been like a transparency marker that's water soluble. That's why water will work very well in this case. So we'll put that mark there, and when it sits in here, you don't want that mark to actually go in the water. So you actually have your dot above the water. And then what happens is, this is a porous paper, and so what happens is the water travels up. Now as that water travels up here, you know, essentially it adds and absorbs into the system, you know, like your sponge does. It does adsorb some too, because it does stay on the outside. So as this water comes up here, the water is also attracted to the various components in that dot. Now, depending how those components are attracted to the water, if they're very attracted, then let's seize the water goes by, like, hey water, look at me, I'm going to come with you. So the water, as the water line goes up, some of that dot goes with it. But if it's, and that could work well for like a red pigment or a yellow pigment. But let's say you're a green pigment that's not very water soluble. I mean, you are somewhat, but not a ton, like you're not that much. Well, then, as this goes up, you know, the yellow would stick with it. You have a dot right with it here. But then the green would have come up, but just not as far. And so it's essentially a balance. It's this balance between, you know, your attraction towards the solvent that is moving up, which is called the mobile phase. And essentially your attraction for the paper that you're like, you know, I just want to stick here. I'm not really attracted to that water. It's called the stationary phase. And so it would just sit there and not move as much. If something's not water soluble at all, it stays right there at the bottom because it ain't going to move. Why would that move? So you could change out your solvent. You could use various different solvents. You could use acetone as a solvent. You could use alcohols as a solvent. You can really design your own solvents. There's a whole field of chemistry developed in order to figure out, well, what solvents are going to work the best. Okay. This is liquid chromatography. You can do this on a bigger scale with columns. You can actually set up these huge glass columns that have these beads in them, this powder, silica powder. And that silica powder, you can drop your stuff on top of it, run your solvent down, and as the solvent goes down the column, the same thing happens. You know, stuff that's really attracted to solvent goes down through it quick. The stuff that's slow goes down. And if you have your column set up pretty big, you can actually see, it's really cool, as it goes down, you see the different actual layers of the thing separated. So if you want something on the top layer that's taking forever to come up, well, that's more solvent time. If it stays at the top and doesn't move, you got another problem on your hands. You're going to need to find a different solvent. One of the biggest techniques that they use nowadays in the chromatography field is called gas chromatography. Gas chromatography works off the same basic principle: stationary phase, mobile phase. With gas, it's a little different. Usually you shoot the system into a cartridge. Okay, and this cartridge could be lots of different compositions. But the basic idea is that there are these small little pores through here. Okay, these small, very rigid, very path-finding kind of pores here that goes through this, okay? And the phase, the solid part of this that it's made out of is sticky, okay? And again, sticky is a relative term depending what you're trying to actually separate out. You can get something more sticky to, like a water vapor, but not as sticky to acetone vapor, for instance. So that really depends on what you're looking for. And what you do is you shoot your gas through here, okay? And again, you still need something to push the gas through. So your unknown gas that you're trying to identify, or your unknown mixture that you're trying to figure out, you will push through, generally speaking, some helium in here if you're in America. If you're over in Europe, you'll probably use nitrogen. Helium's a lot cheaper over here in America. So you push this through, and so that's trying to constantly push these particles through. It's kind of like trying to push all the marbles in through the system. And some get stuck, and so the helium has trouble pushing it through, but some don't. So things that are not very attractive will come through real quick. Some things that are very slow may take a long time to actually come through, but they will come out over time, which is really neat. Okay? And so you can separate them based off their gas. And this can work for things that are, gases at room temperature, or things that are near gases at room temperature. Acetones, alcohols, accelerants for arson fires are actually identified many times through gas chromatography. And gas chromatography is one of the best methods to do that. And so what you could do is you have a little flame on the outside here called a flame ionization detector. Terminology isn't that important. But what it does is it ignites and can tell something's there, and once something's there, you end up getting a proportion of how much was there, especially if it's combustible gas. And so when you're done, you get a time versus proportion kind of graph, essentially. And so it goes wee, 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 And so, you would assume that things that, all things set aside, you'd assume like your lighter stuff comes out here, your heavier stuff comes out near the end. So if you're trying to separate something like methane and octane, C8H18, that's a straight chain octane. And as you're trying to separate those two, you probably predict this is definitely your methane coming through first, and then your octane coming through later. Okay. Next chapter, we'll talk more about another type of detector you can put on there called mass spectrograph. That thing is amazing, and actually does something to the atom and actually breaks it apart and ionizes it. It does some really cool stuff. And they attach those to the ends, and that really gives you even more tools in order to figure out what the identity of the substance is. So gas chromatography is one of the biggest things in analytical chemistry. You can use liquid chromatography. There are lots of types of that. There's more than just the normal liquid. There's ion selective chromatography. There's gel electrophoresis, essentially a form of chromatography that's done by electrical current as opposed to anything else. So chromatography is a very common thing that's used, and it's a tool that chemists and other people will try to use, especially biologists and chemists, in order to get things figured out. So chromatography definitely is one of the coolest techniques that has come out in the modern age. Okay, this concludes part one. I'll pick up on part two for talking about measurements and how do we use those, how do we calculate with them, and what's this stuff about solubility. It's been a long time since that. Catch you here in a little bit. See ya.